instead of having just 40 minutes for the speaker itself, this time we will have 20 minutes for the speaker and 20 minutes for the audience. So we have this kind of a little just timer set up here, in which I will measure the time. Right? So every time he speaks, I will discount his time. Every time you ask questions or you speak, I will discount your time. And ideally, by the end, we should balance out 1-0-0. So please ask questions, please interact, and will make the whole experience much better. With that, your floor is yours.
Okay, thank you. So I'm going to start with a gimmick so that you can use some of your time. So what are some things that we trust when we use computing systems? The floor's open. Yeah. Compiler.
The keyboard.
The keyboard.
The network.
The network.
Operating system.
OS. Ourselves. There's a lot of things. And if you look up in the dictionary what trust means, it'll be described as a firm belief in the reliability, truth, or ability of someone or something, confidence or faith in a person or a thing, or an attribute of a person or a thing. So trust is this thing that we have all the time with, in life, and especially with computing systems. And there's a famous paper that I'm sure many of you have read from Ken Thompson. It's actually his Turing Award speech. And he was thinking about, how we could trust computer systems, and came to a rather pessimistic conclusion. So he sort of came up with this little puzzle, thinking about compilers, and the fact that when we take a program, maybe written in a nice language, maybe a functional language or a high-level language, and then we compile it, we're trusting that compiler to produce a correct binary. But actually, you can imagine all kinds of attacks, and the one that he imagined was one where the compiler is not wrong. In fact, most of the time it does the right thing, but on some inputs, it produces the wrong output. Right? So maybe on certain inputs, it actually does something quite malicious. And so the conclusion he drew is that you really can't trust the code that unless you created all of it yourself. So unless you basically directly wrote the binary that's going to run, on the chip itself, no amount of source level verification or scrutiny will protect you from using untrusted code. And that's a rather it's kind of a downer, especially if you start to think about how many layers of software are stacked on top of each other, and third-party libraries and all kinds of things. It starts to feel like we're sitting on shifting sands. So the same is true of networks. And there's a really fun article that some of you may have read. I encourage you to read it if you haven't. It's from IEEE Spectrum, and it describes an attack that happened around the Olympics in Athens several years ago. And basically there was an attempt to intercept and surveil a number of high-level Greek officials, including politicians. And the way it was done was by cleverly hacking some of the infrastructure that ran the cellular network in a way that was very difficult to detect and took several years to unravel. So I mention this just to sort of motivate that networks have become this really central part of all of our computing systems, and they're this thing that we often sort of have blind trust in. So there is one way out of the quandary that Thompson identified in his Turing Award speech, and it's not a complete solution, but it's a way for us to reduce the amount of code that we have to trust, and that's through verification. And if you go into Tom's talk this morning, he already motivated why verification might be a good idea. And verification takes many forms, but the one that I want you to think about today is something called translation validation, which is an old idea, was really developed quite a bit in the 90s. And the idea is that we don't need to have a perfect compiler. We don't need to build the compiler in a proof assistant like Coq or Isabelle. Instead, we can have the compiler generate for us some kind of evidence that tells us that for a particular input and a particular output, the two go together. So the output correctly encodes the semantics of the input. And then, given this proof and the source program and the target program, we can pass these to some kind of simple checker that will make sure that all three go together. So this is not giving us some kind of like bedrock absolute guarantee that that the program will implement correctly, but it's a way for us to relocate trust in the compiler to trust in a smaller number of parts of the system. Phil.
Wouldn't your checker be subject to exactly the same kind of attack that Ken Thompson described?
That's right. So it's just moving trust around, but the checker itself is presumably simpler than the compiler, so we've perhaps made progress by reducing the size and complexity of the thing that we have to trust.
The size and complexity of the assembly code that you need to look at because you can't trust any source code.
That's right. If we're, the Defense Department or something, we might write the checker using the absolute highest, the most expensive techniques that we can, like writing it directly ourselves.
Okay.
Are you I think it's pretty clear that a compiler is going to be more complicated than the checker. So we've reduced the problem in some scale.
No, the checker has to be right. The compiler doesn't.
Why do you say that?
Well, the whole point of the checker is to get it right, whereas compilers are just running code. Right? Compilers are often not right. You care about whether they're fast. They don't care about whether they're right.
So I think the response I would give to that is that the experience with these kinds of checkers is that they can be quite small, right? Order of hundreds or maybe 1,000 lines of high-level code. And most compilers that I know of are much larger than that. So they do have to be right, but I would argue that they're smaller and simpler artifacts.
Generally you're taking a complex language and reducing it down to a simpler phase, and if you do translation validation along the way, the checker only has to check like a very small set of instructions compared to the language of the source language, which could have much more complexity, provided that you've done translation validation all the way down.
Right. Okay, so I now want to dive in and look at how we might try to do something similar in a network. And I assume that some of you have some experience with networks, but some of you may not. In one slide, what you have to know about networks for this talk is that most networks today have sort of two distinct pieces of functionality. They have a control plane, which is responsible for doing things like discovering the topology of the network, computing paths through that topology, maybe enforcing policies like isolation between maybe different segments of the network. And these control plane programs are often implemented using general purpose languages or very powerful protocols like BGP, which is the routing protocol that runs on the internet. And then below that, all the outcomes of the control plane get communicated to a data plane, which is the part of the network that actually processes packets. So it does things like parse a packet into some kind of structured representation. It then forwards the packet using maybe some routing tables that describe where the packet should go. It might drop some packets. It might make copies of packets. It might encapsulate packets and other new tunneling headers that are being used for certain purposes. So its main purpose is just to sort of implement these kind of simple transformations on packets as dictated by the control plane. And so if you think about what could go wrong in a network, thinking about these two pieces of functionality I think is helpful. The control plane is kind of big and complex. It's typically involves some kind of Turing-complete formalism. Even BGP can simulate Turing machines, at least up to some finite bound. And so trying to think about how we might build control planes in a way that we can reason about them and verify their behavior is more difficult. But the data planes are much simpler and therefore tractable to analyze. So I don't think that we should give up on verifying the full stack, But I want to start by thinking about how we might apply some ideas from verification to the data plane, because that's a problem I think we can solve, and then use that to start building networks where we verified more pieces, including the control plane. Okay, and the vehicle I'm going to use to describe both of these pieces is a new language called P4 that a bunch of us have been working on for several years. So the way to think about P4 is, I already described these sort of two pieces of the network. It's a kind of middle abstraction that sits between the control plane and the data plane. So the control plane, again, might be one of these complicated protocols like BGP, or if you've heard of something called software-defined networking, that's an approach to networking that lets you basically control the network using a C program or a Java program running on a general purpose device. Or there's things called segment routing. So whatever you're doing, you're somehow computing the functionality you want the network to have, and then communicating it down to a bunch of typically custom and fast devices that actually process packets. And if you're using P4, then you have this abstraction that read sort of bottom to top can tell the control plane sort of, this is how I know how to process packets. Or if you're reading it from top to bottom, in the case of, say, software-defined networking, you can think of this as the way that the control plane can tell the data plane how it's going to process packets. So what does this language look like? Well, it's a domain-specific language designed for describing packet processing. So it has some abstractions for doing things like describing how packets are parsed, has a type system that describes how the components of packets, which are headers, get represented, and it has tables, which are a way of describing how packets should be transformed, and also how the control plane can communicate with the data plane in order to manage how those transformations happen. It also has kind of standard features found in imperative languages, so you have type system, you have sort of structured control flow. And the main thing you don't have is anything that would take an unbounded amount of time to execute. So this is very much not a Turing-complete language. The amount of state is bounded and in fact can be statically computed from the program description, and there's no loops. So the total amount of resources needed to process any packet can be computed in advance. Just to give you a little taste, we'll do a demo in a sec. Here's a snippet of P4. That describes an access control list. So this is lifted from a program we'll be looking at in a sec. And basically what this table does is it describes some of the state of the program that's going to be read. So when we're sort of executing this block, there will be some state stored in some structures. In this case, there will be a component IPv4, and we're going to read the source and destination addresses. We're going to look them up with some semantics called longest prefix matching, and then we'll be able to apply some actions. The actions are sort of the stored procedures that get run depending on what the values of these headers are. And in this case, the access control list can either allow or deny. Allow will cause the packet to proceed, and deny will drop it. And we'll have a default of deny. So this is sort of specifying one piece of the processing of the packet in a larger program. And when we actually run this thing dynamically, the table will be filled in with patterns. For example, here's a pattern that matches one of the addresses. Here's a pattern that matches anything. And then any of the actions in the table can be specified. So let me show you an example, a little bit more interesting example of a larger program. I'll show you in pictures first, and then I'll show you some code. So here's a situation where we want to program a device that's sort of going to be a gateway device between some special server with the address that you see on the inside and the rest of the internet. And what we're going to do is set up a couple of these tables. One, you've already seen, the access control table. And then we'll also have a network address translation table, which will map from a public-facing address into the internal address of our server, which perhaps we want to keep secret from the outside world. So if we have a packet that, I think I have an animation for this, a packet that traverses this network, what's going to happen is first the address will get first the packet will get dropped because our access control table came first and the packet had this special address. Sorry, I've got my animations wrong here. Perhaps I'll just jump to the code. Sorry about that. My animations got messed up in changing these slides. So the thing I want you to consider is the order that we apply, the order that we apply these two tables matters, right? So one address is rewriting, one component is rewriting addresses, and one component is doing filtering. And the filtering rules are expressed either in terms of internal or external addresses. So if we do that after translation, there's a different semantics than if we do it before. And this is not a hypothetical example. There was actually an issue in one of Cisco's security appliances where they switched the order of these tables, and it caused a whole bunch of customer configurations to become invalid because they were expressing the filtering, which was important for their security policy, in terms of the unrewritten addresses. And when they moved the tables, suddenly those filtering rules did not have an effect. So let me now show you the same example in code. And I'll jump now to an Emacs buffer. So here's, I need to mirror my displays. Sorry about that. Okay, is that legible in the back? Good, okay. So here's a complete definition of a program that does those two simple functions that I showed you, access control and network address translation. So we start by defining a bunch of types. These types are going to hold the actual bits that are in the packets that are processed by this program, and we can specify things like which fields are in different headers, in this case Ethernet, which is sort of the first header that occurs on most packets, and then IPv4, which is the header that occurs in IPv4 packets. And then we can declare some state variables that hold values of those types. So the first thing our program is going to do is to actually populate those state variables, and we do this by writing a parser. So a parser takes a bit representation of the packet and turns it into this more structured representation. And so we'll write the parser as a little state machine. And the key thing that happens in this state machine is that we can extract certain headers. And the effect of an extract is to sort of grab the next chunk of bits from the actual bit stream, put it into one of these structured representations, and then continue. So this parser will parse an Ethernet header always, and then if the type of the ether type field of the Ethernet header is 800, it will go ahead and parse an IP packet. So the next part of the program declares some of these tables, and in the interest of time, I won't go through these in as much detail as I did on the slides, but essentially the ACL table is as we saw before, and the NAT table reads the destination address only, and then can rewrite the address to a value specified by the control plane, or do nothing.
I'll interrupt you right there,
Great.
just to relieve the ticks on the clock there. So just to make sure that I'm understanding, P4 is going to be running on the data plane, and the control plane might generate P4 to be run on the data plane. You can nod. And it looks like the language goes right down to the low level. Like you'll even define aspects of internet protocols in P4. Mm-hmm. Right. Okay. So how can I get a? I'll need some special hardware, will I, to run P4, or is there a way that a hobbyist could play with it, or a researcher, if not a hobbyist?
Yeah, let me pull up, I have a slide for this. Let me just show you. So P4 is meant to be a sort of target independent low-level but target-independent description of packet processing. And so people have actually built P4 backends that can generate code for any of the actual data planes that you see on the bottom. So one possibility is that you have an existing router chip, and sorry, that's the fixed function ASIC. And in that case, you probably can't program it very much, but at least you can describe what it's doing in P4. So you can think of P4 as sort of a hardware description language, and then you might want to use automated testing, like Tom talked about this morning, to check that your ASIC is implementing the P4 description.
So even if you can't execute P4, you could use it as a description language that can then be used in verification. And yeah.
That's right. And there are large cloud providers are using P4 in exactly this way. So they have routers that aren't programmable, but they're finding it fruitful to describe the behavior of those routers in P4, and then they build the rest of their control plane using the fact that they have a sort of semantics for the data plane expressed in P4.
I yield my time.
Just to say a couple more things. Of course, it's also interesting to actually compile the P4 to a programmable target. So if you have, for example, an FPGA, then you could do that, and there are people doing that. Or if you had a new kind of router chip that can be reprogrammed, then you actually can take a P4 description and reprogram the memories and ALUs and parsers to implement that program. Good question. Okay, so going back to our example, so we have these two tables, and the sort of main part of our program is this control block, which you can sort of just read as if it was sort of main in C or Java. And what it does is it just applies these two tables in sequence. So after parsing the packet, we'll then do access control followed by NAT. And what I've done here is I've annotated the program by hand, for the sake of this example, with some logical formulas that I'm going to use to check that this program is doing what I'd like. So if I want this program to maybe drop traffic going to some IP address, in this case maybe I want my server to actually be isolated from the internet, then what I can do is I can, first I'm going to use a logical variable to remember what the IP address was of the parsed packet, and then I'll apply my tables, and then I'll assert at the end of my program that if the packet was originally destined for this special address, then it should be dropped. And some of you have seen this tool before, but I'll just show you how we can use a program verifier very similar to the ones that Tom talked about this morning if you went to his talk, to verify this program. So I'll tell you more about this program, how this verifier works in a second. But what you see is that this property actually doesn't hold for our program.
Why do you want the packet to be dropped? I thought you were translating it to the server.
Yeah, so I'm sorry, my animation got messed up, so the picture was inaccurate. What I want to do is I want to have these two functions running, but this server I want to keep isolated. So there may be other hosts that should, after filtering, be rewritten to their internal addresses, but this particular server I want to be isolated from the internet because it's some internal server. So, good question, and my fault for messing up the animation. So in this case, the property actually doesn't hold, and by using the model that we get back from the Z3 SMT solver, we can actually get a fairly detailed trace through our program that tells us what kind of packet can cause this property to fail. And in this case, it's a packet that, it's not printed very nice, but it's a packet that has our destination address, but that actually misses in the access control table, and so therefore fails to be dropped. And so if I want to have this program succeed, then what I can do is I have to make some additional assumptions. In this case, I have to assume something about what the control plane is doing. So I need to know the control plane is going to be populating these tables with certain rules. And what I'm going to do is, the first assumption here says that when I have this address 192.168.1.1, then I want to execute the deny action. So that's what this first assumption says. And if I add these assumptions to my verifier, unsurprisingly now, I get that it succeeds because the packets can be dropped. And just to show you quickly that the bug that the Cisco appliance had also would be caught by this tool, if I switch the order of those tables, now even though the access control table has the filtering rule, because the NAT table applies first, the original packet's value might be rewritten, and then we would miss in the ACL table, as this trace shows. So that kind of gives you a taste of P4 and a taste of how automated verification of P4 can work. Okay, so I'm out of time, so I need to now ask you for some guidance. I can show you either one of two things. I can show you a bit under the covers how this verifier works, or I could tell you a bit about reasoning about control planes that we can also do with less automation. How much time does the audience have? About 10 minutes? Okay. Okay. So the way that this tool works is very similar to the general approach that Tom showed us this morning, and actually builds on some of the specific representations and transformations that were developed in work done at DECCIRC and then later by people at MSR. So essentially what we do is we take the P4 program, which describes this bit level description of forwarding behavior, and a description of what we call a control plane interface. So it's these extra assumptions about what the control plane might be doing. And in general, this control plane interface is not so specific as, you know, this particular pattern will be installed in this table. It's a more symbolic constraint on how the program processes packets. We take both these things and we turn them into essentially a standard imperative program written in a language called GCL, and then we transform this representation in several steps, doing some optimizations, and then eventually turn this into a first order formula that we pass off to Z3. So I'll quickly just show you some of these details. So the internal language that we use is, as I said, Dijkstra's guarded command language. If you've seen this before, this will be familiar. If not, I'll quickly run through it. So essentially, it's a language where we have state and we have assignments that can mutate that state. So the second to last element of our production will change the value of a variable by assigning it to an expression. And then we close that under sequential composition and non-deterministic choice. So composition is written with a semicolon and choice is written with these hollow brackets. We can use choice to encode a conditional. We can basically take the two branches of the conditional and then guard them appropriately. And the way we do guarding is by using formulas, in particular assumptions, which essentially you can think of as not terminating or going into an infinite loop if the formula doesn't hold in the current state. And then we also have assertions, which you can think of as blowing up if they don't hold. So we have a front end that can take P4 and turn it into programs in this guarded command language. And you'll notice that there's no loops here, and that's important. And if P4 had loops, we would have to extend this grammar with something like a while loop, which would then make verification more complicated. But because the language is simple, we don't have to do that. And then once we have our programs in this representation, it's fairly straightforward to generate a first order formula that captures the conditions needed to ensure the correctness with respect to one of these specifications. And if you do this in the kind of textbook way, you get very large formulas that can take a long time to solve, even using Z3, as awesome as it is. But there's a really elegant paper by Sachs and Flanagan from Popple 01 that shows a better way to do this. And by using this, Z3 is actually able to handle the formulas that are generated, even for very large programs with many tens of thousands of lines of code. So So far, the story is fairly standard, but there's one piece, which is how do we actually model the control plane? And one way to think about this is that we sort of adopted the slogan that a P4 program is really only half of a program. It specifies, in tedious detail how packets are forwarded, but it doesn't tell us what happens when we come to a table, because the table contents are only chosen by the control plane. So formally, sorry, it's not the next animation. So formally, what we do is we turn tables into a non-deterministic choice between all of their actions or missing. And what that means is that if without any extra assumptions about what the control plane is doing, we have to handle every possible path through the program. But if we know something about what the control plane will be doing, for example, we know that certain kinds of rules will appear in a given table, or more commonly, that groups of tables will be programmed together in some coordinated fashion, then we can express those by adding extra assumptions to our program. And so the way this is done mechanically is by systematically instrumenting the program with extra ghost state. Extra state, which isn't really true state in the packet, but is there for verification. So for example, given one of these tables, like the ACL table, we add a whole bunch of extra state variables. Have we reached this table? Did we successfully look up a value in the table? We call that hitting. Which action did we run? And if any of the actions are parameterized on values that come from the control plane, what were those values? So we have this state in our program already, and then when we apply a table, this gets turned into the mess of code you see on the bottom, which is essentially the key pieces are, you see these hollow brackets on the left, a choice between all the different actions we could have taken, and you'll notice that in addition to actually running the actions, we're updating the ghost state to keep track of where we came from. And so now if we have an assumption, like the one that I showed you, that can be rewritten into just a standard assumption on this extra ghost state. And we can weave this into the program and then ultimately into the formula that we generate. Okay. Any questions about how that works? Oops, sorry. There's a couple of things that are, I think, open research questions to think about. So one is, where do these extra assumptions actually come from? So in our current tool, these things are generated by hand. We have a few heuristics that can generate them automatically, but an area that I think would be quite interesting to look into is how we could synthesize these automatically. There's a lot of work on doing synthesis of these kinds of state, including a very nice paper by Todd Milstein and some collaborators from Stanford, and I think some of those techniques might be applicable to this problem. In particular, we have a lot of data in a network. We can very easily collect traces, and so if you wanted to not go to the trouble of writing these things down, but you had some data that you believed corresponded to the correct behavior, it should be possible to reduce the annotation burden or at least present some options for possible assumptions that could be made. Okay, so I think I'm out of time and I think the audience is close to out of time. So I'm going to skip over the work on control plane verification that I had prepared. If people are interested, I'm happy to talk about that offline. And I'll just tell you a little bit about the road forward. So there's a new project that we've just started up earlier this year at Cornell. And what we're doing is we're trying to write down a formal semantics for the P4 language. P4 has, like a lot of industrial languages, a very detailed but ultimately informal spec. So it's a combination of sort of very precise definitions of bit formats and abstract machines for how the parser works and so on, combined with dozens of pages of English prose that are not as precise in parts and sometimes contradict each other. And so the language is so simple, and the PL community over the last 50 years has developed such rich techniques for modeling languages. We think it's a shame not to have a mechanical and formal description of the P4 language. And in fact, I think the lack of a formal spec is holding back development of the language. So there's a lot of interest in exploring various extensions, both of the type system and of the underlying programming constructs. And right now it's not easy to know if adding those new things will break some existing properties of the language. For example, this property that every program can be executed in constant time. That's a very important thing. If we break that, then it won't be possible to compile P4 to some of the devices that we want to, and it'd be easy to break that property by accidentally allowing ourselves, some way to express a recursive definition or something else. So by having a formal semantics, we'll be able to answer these things directly. The other reason that we're doing this is we're quite interested in building verified compilers. And so to start with, we're actually building a verified compiler using translation validation. There's an existing compiler that targets eBPF, which is the packet processing, one of the packet processing components supported by the Linux kernel. And we're also interested in generating verified hardware designs using a deductive proof of system. And we're actually doing this, this tool is already being used by several people outside of Cornell. So if you're interested in P4 and would like to get involved, please get in touch. We'd love to have contributors and people using this. And stepping back, I think, as the title of my talk sort of indicated, I think networks are a really fun place to work because they have both sort of the simplicity as exemplified by the data plane, but also the richness and complexity as exemplified by the scale and the control planes. And so there's a kind of nice tension and increasingly clean interfaces between these pieces that makes it a fun place to apply ideas from formal methods. So if you're a student or someone looking to get into this area, I think it's a really fun and rich place to work. And I also believe that the network is an ideal place to sort of do this kind of work because you can think of the network as sort of being the glue that sits between all of our different computational units. And so if you're doing something like wrapping a component of a system maybe with a reference monitor or wanting to check a certain property, enforcing that using programmable networks may be an attractive way to go. Okay, so I think I'll stop there. This is work done with lots of collaborators at Cornell and Barefoot and several other places. And if you're interested in papers, you can find them on my website. So thank you.
That was an interesting talk. One of the things that interests me is not just the behavior of the network, it's the physical structure of the network. Can you comment more about how you might think that the type systems you might be wanting to develop with the formal verification could help towards that?
Can you explain what you mean by structure? I'm not quite sure.
So for me, the structure, if I say I have a communication network, there might be a fixed number of nodes, each connected to each other through maybe one or multiple channels, and you want to sort of ensure that that's the network description you're expecting, or the structure of it, can only be that, and you can't have any deviation from that description.
So let me try and give an answer. I'm not sure if this is going to exactly what you're thinking about. But one thing, so this work I showed you was very much concerned with the kind of simple and stateless processing that you tend to see on routers. But if you jump up to applications, there we typically think of things more like protocols with state machines, and so there seems to be a mismatch between those two views. I didn't cover this, but it is possible to encode state in P4, and there are some people who are thinking about how we can take application level protocols, formalized using state machines, and actually push those down to P4. I think it would be interesting to think about how you could apply verification there. Perhaps using a tool like this sort of just works. Perhaps some additional work is needed to make it scale, or I should say, like, our tool handles the state that P4 has, but it does so in a kind of, it basically farms it off to Z3. So if Z3 can handle the state, then you get the answer you want, and if not, then you have to add some extra assumptions. So I think this is a fruitful place to look, and it would be, I mean, I think the state of the art right now is basically that people are trying to take application level programs and sort of push them into, onto these network devices. And it's, the first few are kind of quite simple and sort of, you know, just work. But more generally thinking of the network as kind of this maybe hypervisor that sits between the components, and we want to actually express these protocols and then and check for conformance. I think that's a great thing to do. Let me say one more thing. There's a beautiful paper out of CMU that does this, focused on home networks and IoT. So probably many of you have a bunch of devices in your house now that you've plugged into your home network. And if you're careful, maybe you actually set up a separate network for the untrusted, you know, marketed in, manufactured in countries with unknown provenance of the components. And you want to keep that separate from, you know, your own laptop. And so if you've done that, what you're basically doing is saying, I want the network to keep these two devices from actually talking to each other, or only to go through a gateway and, you know, not to be accessible to the world. So I think that kind of logic, you know, if you start out with kind of simple slicing and isolation, it's pretty simple. If you think about actually checking the kinds of protocols that are richer, then it gets more interesting.